Welcome to the second in a series of screencasts on the subject of acids and bases for the module CHE10063. So today what we're going to do is we're going to talk about the strength of acids and bases and how we can measure that and how we can define it. The reading for today, so the associated resources, you've got inorganic chemistry pages 151 to 153 and elements of physchem page 196 to 198. There's also a table I believe is on page 199 which might be useful too. But as before, the lecture notes should hopefully be pretty comprehensive. Okay, so last time we introduced Ka as an idea of how strong an acid is. Okay, Ka being the acid dissociation constant. So a large value of Ka would indicate that the equilibrium equation that we wrote out for the dissociation of an acid, AH, okay, by reacting with water into H3O plus and A minus. If Ka is a large number, then basically that equilibrium is going to be further to the right, so there'll be more products, and obviously if Ka is smaller, it'll be the opposite. The equilibrium will sit closer to the left and there'll be far greater concentration of reactants than products. Okay, and of course Ka, as with many equilibrium constants, varies by many orders of magnitude, and for that reason it's more convenient to refer to pKa. Okay, so that's what it says here. So pKa, we use a logarithmic scale to refer to pKa. Now, if you're not very familiar with logarithms, there will soon be coming some screencasts on that exact subject. So just hold fire for now, and we'll have some screencasts that will sort of increase your understanding with it. But just simply put, if we say pKa is equal to minus log to the base 10 of Ka, then that also means that Ka is found when you raise 10 to the power of minus pKa. Okay, so for example, if you had a pKa of 1, then your Ka would be equal to 10 to the minus 1. For example, which is 0.1. Which is actually a relatively big number. And you've already encountered logarithmic scales before. So you've already met with the logarithmic scale for pH, which is minus log to the base 10 of the concentration of H3O plus ions. Okay, and we can also extend this to other types of equilibrium constant that we've already seen. So for example, this is the equilibrium constant that it sort of describes the autoprotolysis of water, Kw, and we can say pKw is equal to minus log to the base 10 of Kw. So basically this P, that really means minus log to the base 10. Okay. Now once we've done that, we can start setting up a pKa scale for acids, and this is what we normally refer to. We don't normally refer to the Ka of an acid because that can vary over 10 to the minus from 10 to the sort of minus 20 all the way up to 10 to the 10, which is quite a big variation. Obviously, we refer to pKa in this case. So this is a pKa scale, and on the left hand side of the scale, what you get is you get really very acidic species. Okay, so this would be things like superacids. You may not have heard of these, but these are acids that are stronger than things like sulfuric acid. Okay, and these are where essentially for example, sulfuric acid has been tuned. So in this case, you've had a CF3 group put in place of one of the O's. One of the OHs, sorry, and that in doing that, it's made this proton much more able to dissociate than it is in just straight sulfuric acid. Okay, and we'll talk a bit about that when we start talking about oxoacids later on in the course. But superacids are, the strongest acids that are known, and these are often the subject of industrial research. Okay, you then have strong acids, and these are the ones that you probably have met before. So things like sulfuric acid, hydrochloric acid, nitric acid. These are things that have pKa that is sort of less than 0. Okay. And then as we go past 0, we start getting weak acids. Now, obviously, if its pKa is 0.1, it's right on the boundary. So, it's still sort of technically a weak acid via the definition I'm providing you here, but there's going to be a strong weak acid, if that makes any sense. Generally speaking, weak acids have pKa's that are, quite a bit less than 0. We're talking like 2 or 3 or, all the way up to, 6, 7. 8 maybe even. And in this case, we've got, your weak acids, so things like, ethanoic acid. I think this is ethanoic acid here, methanoic acid. And we've got, other species like carbonic acid and citric acid. Okay. As you keep going down the scale, you're getting towards weaker acids, but in doing that, what's happening is the strength of the conjugate base, so is going to get stronger. Okay, so here we have a weak acid, but in this case the conjugate base is weaker still. Okay, but here as we move towards weaker acids, as the acids get weaker and the pKa gets bigger, the bases become stronger, and eventually, sort of when we get around about the 14, 15 mark, we start to consider those strong bases. So for example, KOH, the H2O part of that, if we consider water to be an acid here, that would have a pKa of 15. Okay, there are other stronger bases. Okay, so things like species that you will meet later in your course and perhaps in the second year will be things like N-butyl lithium, and this one is, for example, a very, very strong base indeed, and this is capable of deprotonating just species just containing carbon and hydrogen. Okay, and so in that case you've got a pKa that's greater than 50, which is a pretty big pKa, and there are other examples of these too. Okay, but generally speaking, we've got a pKa scale. Key points are, that if it's a negative number, it's a strong acid. If it's a very big negative number, it's a super acid, and that anything bigger than 0 is a weak acid in terms of its pKa. Okay. Okay, so if you remember, we basically said that we could define, if we knew the Ka of an acid, we could also know the Kb of that acid through the relationship with the autoprotolysis constant for water. Okay, and that was equal to 10 to the minus 14. Yeah. Okay, and that was at room temperature. Yeah, and it meant that basically, if one of these gets, if Ka gets bigger, then Kb has to be smaller, and this is the Kb for the conjugate base of the acid. Okay, so what we can do is we can basically say, well, what about log Kw? Okay, so we can go log Kw is equal to, we're going to take logs of both sides, Ka, Kb. Yeah. Now, there's a law of logs that basically says that if you multiply, if you have a log of A multiplied by B, that's the same as log A plus log B. Okay, so that's a key law of logs that you can sort of remember. So let's deal with that. Let's put that into practice here. We can end up with log Ka plus log Kb. Yeah. Okay. All right. And then what we can do, because we know what, we've already defined pKw, for example, or indeed pKa is equal to minus log to the base 10 of Kw. And incidentally, I'm just going to go in and put in the tens here. Generally speaking, in chemistry, when we write log, we usually mean log to the base 10, and sometimes you'll see that the 10 gets lost, as I did there. If we want to refer to, there are other types of logs. There's another special type of log called ln, and that would be essentially ln x, and that refers to the natural log, and that's where the base is equal to e. Okay, so in this case you've got base is equal to 10, in this case you've got base is equal to e, where e is Euler's number. Again, this will be covered in the screencast later on, and I'm just kind of, giving you an idea now. Okay, so let's just, basically what we have to do is we have to multiply both sides by minus 1. So let's just times by minus 1, and we're going to get minus log to the base 10 of Kw is equal to minus log to the base 10 of Ka minus, because a minus times a minus is a plus, a minus times a plus is a minus even, log to the base 10 Kb. Now this one is equal to pKa, this one is equal to pKb, this should be a B, pKb, and of course this one is equal to pKw. So we can say pKw is equal to pKa plus pKb. Oh, I've just written A again despite saying B, yeah? Key point is, again, as before with the equation for Ka and Kb, we can also say that if we know the pKa, we can calculate or find the pKb of the conjugate base, or vice versa. If you know the pKb of a base, you can and you can calculate the pKa of the conjugate acid. Okay. Okay, so to sort of sum this up, we need to think back to our equilibrium equation. Okay, so I'm going to write it out up here. I'll just get a good colour. Okay, so we've got AH plus H2O, and we're going to put the state symbols in, is in equilibrium, and it's very important that we use this equilibrium arrow. H3O plus AQ plus A minus. Yep. Okay. Okay. Right. A strong acid is one where the equilibrium lies on the right hand side. So the concentration of products is higher than the concentration of reactants. A weak acid is the opposite. The equilibrium will lie on the left hand side, and the concentration of the undissociated species at equilibrium, that's AH at equilibrium, is going to be much greater than the concentration of the dissociated species A minus at equilibrium. Okay, so it's not completely dissociated. Yeah. And we've already defined how we can sort of describe that in terms of pKa. And my definition here is this: that a strong acid has a pKa that is less than 0, and a weak acid that is an acid that has a pKa that is greater than 0. Okay. Okay, so to finish this screencast, I want to go through a worked example of a calculation that involves a weak acid. So this is something whereby we can calculate out the strength of the acid, or we can calculate out the fraction dissociated. Okay, so what we do is we start with an acid of known pKa, as it says here, and we want to find the fraction of acid that's been dissociated at a given pH. And in order to do this, we need to follow a stepwise process. Okay. And this stepwise process is pretty clear. So the first thing we need to do is we need to get information from the question. So we need to write out the equation for the reaction. We need to write out the equation for Ka. And we need to obtain any information we've got in the question at the beginning. Okay. And this, to be honest, this here idea of getting out information from a question is something you should be doing for any physical chemistry questions that you have to answer. After that, we need to make certain assumptions. The first thing we need to do is we need to say, okay, if there is no other buffer, now a buffer is a salt, and it's in this case it would be A minus. Okay, so if there's no other buffer present, the concentration of H3O plus is equal to the concentration of A minus, and that's because if I just quickly write it up here, you've got HA aqueous plus H2O in equilibrium with H3O plus aqueous, that's a liquid, plus A minus. Now both H3O plus and A minus on the right hand side have come from the dissociation of HA, and when 1 mole of HA dissociates, it will liberate 1 mole of H3O plus and 1 mole of A minus. Okay, so the concentration of these two, if you haven't got any additional A minus already added from just putting in a salt, like the buffer in this case, is going to be the same. Okay, so this is something we need to make an approximation of. It's not an approximation really, it's a sensible assumption if there's no buffer in there. After this, we can calculate the concentration of HA because we've got Ka and we've got the other information. Okay, and I'll show you how to do that in a minute. And finally, we can use this equation here. Fraction dissociated is equal to the concentration of the dissociated species plus the concentration of the dissociated species plus the concentration of divided by, stab back a bit, the fraction dissociated is equal to the concentration of the dissociated species divided by the sum of the concentration of the dissociated species plus the species that has yet to dissociate. Now this is often referred to, or in this notes anyway, I refer to this as HA initial, okay? So this was the concentration of acid that you made up right at the start, okay? And that's what's written down here. Okay, so for example, I took, a number of grams of my solid acid. I dissolved it into water, and then the equilibrium occurred. And so that after the equilibrium, these are the concentrations A minus and HA. Before the equilibrium started, you have a concentration of undissociated acid that's the initial concentration. So hopefully that makes sense, but we'll see it in action now. Okay, so this is the worked example, and this is a typical question, okay? So here we have HBr, which is, as you can see, a superacid. Let's write that with a different color, superacid, or a very strong acid, anyway. It's added to water until pH is equal to that. Now, because this is a superacid, you might have an idea of the numbers we're going to get already. You know, you're going to get quite a big fraction of HBr dissociated. But nevertheless, let's go through the process, yeah? So we've got pH, so therefore we can work out, other things too. But nevertheless, let's go back to the process. So step one, write out the equation for the reaction. Okay, so let's write that out. HBr AQ plus H2O liquid equilibrium arrow H3O plus AQ plus Br minus AQ. Okay, and we can also write out an equilibrium equation. So that would be Ka is equal to concentration of H3O plus concentration of Br minus all over the concentration of HBr that hasn't dissociated at equilibrium. These are all numbers at equilibrium. Okay. Next, we have to obtain information from the equation, from the question. Sorry. Okay, so we've got pKa, pH and pKa. So pKa is equal to -9. So we can say Ka is equal to 10 to the minus 9, which is 10 to the 9. Okay, so that's a very big number of Ka. And again, should be giving you an idea that the equilibrium is going to be significantly to the right, and the fraction of HBr that's dissociated is going to be pretty close to 1, isn't it? pH is equal to 2, and therefore concentration of H3O plus is equal to 10 to the minus 2, and of course that has a unit because it's a concentration, moles per decimeter cubed. Okay. Right. The next thing we have to do is we have to say that the concentration of H3O plus and the concentration of Br minus are the same, and that's for the reason that we said already. Okay, so we could say concentration of Br minus is equal to concentration of H3O plus, which is equal to 10 to the minus 2 moles. And I'm going to say moles per litre actually, because this was the convention we've been using all the way through. But decimeters cubed are the same as litres, aren't they? Okay. We could also write molar, yeah, and that will be capital M. These two things are equivalent, yeah. Okay. So now what we can do is we can rearrange the equilibrium equation. Okay, so we can say concentration of HBr that's not dissociated is equal to the concentration of H3O plus concentration of Br minus over Ka, which is equal to 10 to the minus 2 times by 10 to the minus 2 over 10 to the 9. Yeah, let's just write that out again because it was a bit sloppy. 10 to the 9. Okay, and that is equal to 10 to the minus 13. Yeah. And that's obviously got units of molar as well. Okay, so what we can then do, and this is here is our answer here, 10 to the minus 13. We can say that all of the moles of Br minus and HBr came from the Br anode initially, so we can calculate our HBr initial. And so we can say that the concentration of Br minus is equal to, we've already written that, it's equal to 10 to the minus 2 molar. The concentration we just calculated out this at equilibrium is equal to 10 to the minus 13 molar. And so therefore, the sum of these two here is effectively 10 to the minus 2 molar, with quite a few zeros and a 1 right at the end. But this is the same as that, isn't it? So now we can calculate the fraction dissociated, and we can just basically say it's 10 to the minus 2 divided by 10 to the minus 2, which is equal to 1, and so that's fully dissociated. Okay, and I'll give you an opportunity to practice this in one of the quizzes that will be online soon. Okay, so just to summarize, we've talked about both strong and weak acids, and we've said that a strong acid is going to almost completely dissociate or completely dissociate in water if it's a superacid. Okay, and so in that case what we can do is we can show that with a direct arrow, a reaction arrow that you're familiar with. That's okay if you're talking about a strong acid. However, we've seen that a weak acid, and you'll see this when you try the example in the quiz, you should not get a fraction dissociated that is 1. You're going to get something significantly less than that. See, a weak acid is incompletely dissociated in water. Okay, and in that case, you need to use the equilibrium arrow because the equilibrium often lies on the left-hand side. Okay. Key point here, and this is a really important thing that people often do, is not to confuse acid strength, which is the position of the equilibrium, and concentration, which is related to the pH. Okay, and that tells us how much of everything is in solution, doesn't it? Okay, whereas strength is how much it's dissociated. And finally, with that in mind, you have to use the same concentration of concentration, and when we talk about concentration here, we're talking about concentration of HA initial, the same initial concentration made up in order to compare acid strengths, because only then, by measuring the pH, would you be able to tell how much the acid has dissociated, and from that get an idea of the acid strength.